Morning. I want to make sure everybody's awake today. I've got jumper cables in the truck if the coffee's not working. I'm Mike Pappas, W9CN. I'm with Edge of Space Sciences Group. We're not the Chinese balloon guys. See, I knew somebody'd get that joke. I just had to throw it out there. We've got a couple of other ballooniacs here with us today. Larry Noble and Jeff and Tom are part of the balloon nut group. Well, this is kind of interesting. The remote doesn't remote. That's all right. We'll do it the old-fashioned way here. That didn't remote either. So I'm going to do the presentation. Anyway, I'm been a ham for about 25 years now, and got looped into USS back around flight 120 or so, 117. We're at 334 today. Larry's been around for a very long period of time. We have some new people that we've sucked into our sphere, like Jeff, who is one of the brainiacs that writes our track and predict software, and also runs our ground station. Under the heading of geniuses, I'm part of the crew that just goes out, drags our knuckles around on the eastern plains of Colorado and finds stuff. He makes it possible to stand by the side of the road and go, oh, it's landing right here. Larry, on the other hand, is our gas passer, if you remember MASH. He's responsible for making sure that we have sufficient fills. Balloons meet the targeted ascent rate, which is very important for us to figure out where it's going to land. If we have the wrong ascent rates, we either come up short. If we have a really wrong ascent rate, we'll end up in Nebraska, which of course can be problematic. And it's magic on both sides of that to get that all to work. We started off a long time ago with doing LORAN. Anybody remember LORAN? And DFing. And now we literally have such good tech that we're usually within a quarter mile of where it's landing. And we get students come out and they're like, wow, this is cool. And we're like, look right there, it's coming down. I joked one day, when I was alphaing, I told one of our team leaders to drive down this road about 1.5 miles, open up the back door of their car, and the payload was going to fly right in. So we got close. And everybody was like, this is cool. All right, so let's, yes, this works. Perfect. So, hang on. Perfect. So, as one of the track and recovery guys, I have a Doppler Systems DF rig. And it consists of a couple of parts, a summer and some brainiacs. But the real key to this thing is there's an AOR scanner that sits in the middle of this, and it tunes up and it says, I'm listening for beacons. And I cooked it. So the VHF side went from about minus 120 to 12 dB SYNAD to about minus 80, which kind of rendered it useless. And of course, it did this in the middle of COVID, right? So, AOR had closed their repair facility in Southern California, which meant I had to send it back to them so they could send it back to Japan, so they could fix it, so they could send it back to the US, so they could send it back to me. And that little project took 2 months and $140. And as part of this, I needed to figure out why this was happening and how I was going to keep from doing it again. There's a picture of the display that's mounted on it's double-sided gorilla taped to the dashboard of my truck. And what's really nice about it is when it's all working and very happy, you literally drive down the road, the compass goes, it's right over there. And you get out of the truck and you go, it's right over there. So it's really handy, especially if we have a bad day with the OSS and we lose APRS beacons. Never happens. Don't jinx it. Then we're going to use DF. And there's a picture of the backside of the AOR. The interesting part here is this multi-pin connector feeds an RSSI signal to the DF system. So the bar graph that you guys saw in the previous image there is driven off the RSSI coming off the AOR scanner. That also tells the DF system that it has a valid signal. So it won't provide a bearing unless it has valid data. So you just can't throw anything at it. Otherwise, this wouldn't be a giant problem. The truck's got more than a few radios. A couple of FT8900s. One is dedicated for APRS only. And that runs 5 watts. We don't need any giant amount of power on APRS. And we'll get to the reason why. We have a couple of DMR radios. We also carry our own SLR 5700 DMR repeater in the truck. And that's linked via LTE to RMHAM wide and central, which is a unique experience. We have an SDR ADS-B aircraft receiver. So we always fly ADS-B beacons, right? So aircraft know where we are. And then on the ground, we also can use that as a backup in case the world really comes to an end. And then we have an SDR-based APRS, 6-channel APRS receiver that looks at all of our beacons have an APRS burst at the end of them. So if we lose the primary APRS beacons, we can use that burst into our SDR receiver into Jeff's Magic Linux-based bricks in all of our vehicles to get lat launch and altitude. We carry a Cradle Point IBR 1100 LTE modem, which is on Verizon. That gets us the links to the world. And of course, with that, you have lots of antennas. That's the SLR 5700 running a MikroTik VPN, which links back into RMHAM. It's a unique experience to be driving down the road and know that you've never outdriven your repeater coverage as long as you have cell service. And that's turned way down on power. And on top of that, we're using a really cheap duplexer here. So output of the duplexer is about 4 watts. So, you know, we have so much other RF going around on the truck. The last thing we really needed was more. And for us to use handhelds in the field, it's good for 3 or 4 miles. Mobiles, 5, 6, 7, 8, 9, 10. Kind of depends on where we're parked. We usually try to find a high spot. This is the top of the Ford Excursion that we drive. The DF antennas are on the back side of the vehicle, and we tried to space those as far back as we could and maintain enough ground plane around them so that their pattern's reasonable. Because if the backside of the pattern's all screwy, the DF system is going to have a reduced sensitivity off the backside of the vehicle. And then on the front half here are all the emitters with some interesting stuff in the middle. The real short stubby here is ADS-B, which is at 1.0 something gig. So it's only that tall. And then this is our 6-channel receive-only SDR antenna, which is a 1/4 wave, 2-meter whip. And we'll talk about the problems with those in a minute. And then the front's got a bunch of, it has 5, here, we'll just go to the next slide. It's got 5 Larson dual band antennas. Now, the reason we did dual band was twofold. A, we were lazy. And B, it allows us to plug any radio into a spigot and know that it's going to work, right? Not a particularly inexpensive solution, but like I said, we were lazy and it worked. These two are Wi-Fi, 2.4 gig Wi-Fi ports. This is our LTE antenna. And then back here is a Garmin puck for GPS. And we take that and distribute that GPS data as RS-232 around the truck to all the stuff that needs GPS. So what was killing the AOR is probably a lack of isolation between the one of the radios and the AOR. So the question is, how do we figure that out? And the answer is measure it. And so we cracked out our vector network analyzer and did a whole bunch of testing, right? So that's the test setup. And of course, I decided to do this paper and got accepted to do the paper, and it's 20 degrees outside, and I'm sitting in the truck making the measurements, right? So I'm out there in a parka, and I'm trying to keep the feeling in the end of my fingers while I'm doing all this stuff. And of course, when you do this, then you generate a lot of data, right? And as part of this, not only did we make all these measurements, but we took screenshots off the vector network analyzer so we could, match all that stuff up. And, that's a lot of testing, okay? So results, let's look at VHF test results. So from the driver's side front DF antenna to the driver's side rear Larsen dual band, the isolation in the VHF band measured across all 4 meg of the band is 16 dB, okay? And if you go to the passenger side front to that driver's side back antenna, it's 22. Now, that seems like a lot, but when we look at this from so here's a diagram of what that test looked like, right? Front to rear, passenger to rear, and then the back sides. You'll notice there's a relatively good sized jump between the front DF antenna and the back DF antenna in terms of how much isolation you get. We go from 16 to 24, which is, now we're starting to get into good numbers here. But the reality is these two are our most problematic antennas in terms of isolation. So if we have a 50 watt VHF radio into the antenna that's nearest the DF antenna, it's going to generate 1 watt of RF into the DF system. And I'd like to thank Willem for double checking my math on this, but here's how this works. 50 watts is 46.99 dBm. So if we convert this all to dBm, then it's a real easy little math problem, right? So we take 46.99, we subtract the isolation, which is 16.19. Resultant RF power is plus 30.8 dBm, right? We know that plus 30 is 1 watt, right? So the reality is it's 1.2 watts of RF energy going into the summer on the DF system, which then presents that RF to the input of the AOR. Now the AOR on a really good day, wind behind its back, is plus 10. So we're overloading the front end of the AOR by 20 dB. All right? And that's not good for it. And again, thanks to Willem for double checking all my math. The last thing I want to do is present all this data and go, you're off by a couple of dB. We also ran the same isolation test on UHF. Now, our advantage with UHF is it's a lot better. So we went from 16 to 32 dB of isolation right out of the gate. Bingo. Okay, doubled our isolation. And on the passenger side, it got a little better, a couple of dB better. And there's some variability here. I went out and did this testing over 3 days and always go back to a gold standard, right? Let's do this first test that we've already got in the book, and let's run it again, and let's just see if it's, is our test setup the same? And the reality is things move, especially in that kind of weather. And I also didn't want to park it out in the middle of my field, because then I'd have to run the engine to keep warm. As it was, I just ran a long extension cord out and threw a little heater in the truck to try to keep the frostbite down. But the reality is that it was parked relatively near the house. There's some reflections there. And all these test results varied by a couple of dB. Welcome to the real world, okay? Here's the UHF test result diagram. Again, doubled the isolation. So let's look at what that looks like when we run the math. So if we run a 40 watt DMR radio into this thing, it's 46.02 dBm. Again, thanks, Willem. We subtract out the isolation, worst case isolation, which is 32 dB. And then we end up with 13.8 dBm into the antenna, which is about 3 dB more than the AOR really wants to see, okay? And long term, that's not a good plan, which is probably what cooked the AOR. And just for giggles, I also measured, while we have the test set up, right? We may as well test everything else. And I ran some VSWR sweeps. So I measured to the front antenna on VHF. You're looking at 24 dB of isolation, 18 here. So it's a couple of dB better than the back antennas, but it's not at VHF frequencies a giant step, okay? If we look at that on UHF isolation, 40, 38s, again, it's a couple of dB better, but it's not 50. And then if we look at the front center antenna, again, we're just incrementally getting more isolation. Again, on UHF, you're in the starting to eclipse 50, but here's the interesting part. The back antennas get worse by a couple of dB. Okay, now if you do the math calculation, right? Let's calculate the math. Let's do the wavelength thing, right? The reality is the calculations are off by anywhere from 10 to 20 dB over what you actually measured. Measurements are actually better than the calculations. The only thing I can think of that's causing that is we are so near field that the waveforms haven't fully developed. And if you look at the literature on this, people want to make these measurements at 10 wavelengths. So at 2 meters, that's like, you're 20 meters out. There's no way this makes any sense. The basis is we've got to get this to work on the top of the vehicle as it is. So you throw the calculations right out. Let's just make a bunch of measurements and see where we're at.
Things don't tend to stabilize when you're looking at the field strength indications. Those field strength indications go with magnetic flux. So that's going to change. The closer you are to the antenna, the more stable that flux point is. So it's going to get strange the closer you are. That's why they do it at 10 wavelengths out, because things tend to mellow out a little more and be a little more stable the further you get away.
Well, and that was the funny part. So I got these values, and I was like, maybe something's wrong here. So, of course, I go back and recheck all of it and test it again. Well, because, you have bad connector, there's a whole series of things that could potentially go wrong when you're doing field measurements. And you want to go back and say, okay, so I measured these, and these all came up within a dB of the original measurements, and then went to the backs and came up with pretty close to the exact same numbers. VSWR data. So this is one of our quarter wave VHF DF antennas. And I've swept it over the whole UHF band. And that's what its VSWR looks like. So quarter wave VHF antenna measured into the UHF band. Mid-band VSWR is 7.4 to 1. And the best this ever gets is, about 2. But your radiation efficiency is non-existent. Just because it looks like a good load doesn't mean it's going to work. One of our 70 centimeter dual band antennas swept on the 70 centimeter band, all 30 megabit, right? That's a pretty big leap for an antenna. Shows that mid-band, it's 1.71. There's some bumps here in areas that you're probably not going to use that antenna in, which is probably why Larson put them there. Through where we normally use most all of that, it's very well behaved.
Mike, a question from the chat.
Yes.
Was the loss through the antenna summer to the AOR characterized?
Loss through? No, it wasn't. I only measured it at the ends of the antenna cables that go into the summer. That's an interesting question. I suspect it's probably a couple of dB through the summer. There's a preamp in the summer that's supposed to make up for some of that, but I never looked at it that way. An interesting point about the 2-meter whips is they're cut long. So they ship from the factory at the low end of the band. And so if you're going to use them in the higher end of the band, you want to get my hair cut. Okay? Just while we were out there. Yeah. No, yeah, literally we're talking about maybe an eighth, a quarter. You just kind of have to play with it. I manually trimmed a couple of those, and it was, you just, a little bit went a very long way. And if you cut them too short, you can't go back. And with the DF system, the cable lengths on the NMO mounts to the summer and the antennas all have to be as tightly matched as possible. So the system becomes as symmetrical as possible. Literally an eighth of an inch. So what did we learn? All right, so certainly do not run VHF in the back antennas. And certainly don't, if you're going to do that, don't run anywhere near 50 watts, like maybe 10, right? Only run UHF in the back antennas. And I ended up putting a 3 dB inline pad on the input to the AOR, just because I don't think it needed another round trip to Japan. What have we learned? We haven't killed any radios or SDR dongles. Yay. The APRS is only running 5 watts. That's at the far end of the duplexer. It's actually a little less than that, about 4 watts. More spacing is always better. If you can do it, single band antennas are better, so you can work the inherent mismatch between the antennas. That's a good plan. If you can do any sort of vertical separation, trunk lid versus roof kind of thing, that's good for 6, 7, 8, 9, 10 dB worth. Anything. Get anything. You know, if you've got antennas mounted this close together and you're running 40-watt radios, no good comes from that. Okay? Don't fender mount VHF antennas. It's just bad. You get a wildly asymmetrical pattern. They don't load particularly well. And the side that's on the fender, that side's not getting any energy, okay? All the energy is going across the front of the vehicle. Not good. You know, our preference is to use NMO mounts on everything. Okay, get the 3/4-inch hole saw out and knock them in there. It will not reduce the resale value on your truck when you trade it in at 190,000 miles. Trust me. It won't make any difference. The only other thing is about every 2 or 3 years, we get on the top of the truck, we take all the antennas off, and we tighten all the NMO mounts back up because we blast down washboarded roads all over the eastern plains of Colorado, and those things all loosen up. So we have a party usually every couple of years just to secure them back down. The way we know they're loose is when we see water dripping into the cab. Just questions?
Which is just use really crappy coax and all of your isolation problems go away.
Well, Willem, it's a brilliant solution. The problem, of course, is that we're looking for telemetry on balloons on our APRS receive, and those things are at 105,000 feet up, and that transmitter is 100 milliwatts. So you're listening for a 2-meter signal that's 20 miles away at 100 milliwatts. And let me just come circle that story back around. We no longer use VHF for comms in the field, period. And there's several reasons for it. First off, one, it desenses your APRS receive. So every packet that we miss from the balloon doesn't make it into our Genius's prediction software, which means that our radius of inaccuracy rapidly goes up. And we used to be really happy if we were within 10 miles of where the balloon lands. Now I complain if I'm greater than a mile away from the balloon. So that's one problem. The next problem is we did a vehicle clinic a year or so ago. We brought in all the track and recovery vehicles and their owners, and we did a complete survey on all those vehicles. We used an Aeroflex to test all their radios. We used my vector network analyzer to sweep all their antennas. We looked at their power systems. We updated their software in their systems. And out of all those vehicles that we tested, there wasn't a single one of them that had a VHF install that was less than 3-to-1. Okay? So if you're running VHF, you got to be on top of your game there, because otherwise it doesn't work. And the other problem you run into with VHF is the use of handhelds. The radiation efficiency on a handheld is about 10 dB less in VHF than it is on UHF. And that's, again, because there's not enough ground plane. It's physics.
Question from the chat. Does the AOR front end have to be active to be susceptible to damage? In other words, if you power it off, is that protected?
No, and when I blew it up 3 ICs and a transistor in the front end. So it chewed a bunch of that stuff up. Yep. And yes. Any other questions?
One interesting note, if you guys run Doppler systems, they have some rules of thumb for spacing between transmitters and receivers. And one of the interesting things is our PhDs here that are really good in math couldn't figure out their calculations. But basically what it comes down to is don't run VHF if you're trying to DF VHF, and run as low power as possible on your transmitter devices. In fact, they suggest use a handheld inside the vehicle instead of a radiator on the top of the trucks. It's just good food for thought. And we have a lot of them, so we've tried to figure out the best solution for it, and it's generally running a handheld in the vehicle if you're trying to DF from your roof.
We've had really good luck with that system, and that the system never turns off in the vehicle, so it's running all the time, and it's been running all the time now for about 10 years, which is a long time to be bounced down a road, and it's been very, very reliable. Jeff.
Did you have any observations about ground plane do the dual band antennas, are they more sensitive or less sensitive to ground plane than of course a single band whip antenna?
It's a really good question, and I haven't seen any giant variation, but I haven't looked for it either.
Yeah.
And I wasn't, when we laid out the roof of the truck, which took a couple of days, and we took the whole interior of the truck out to do it, because the other problem you run into is there are structural ribs that run under there that you don't see. And you're like, oh, we did the math, this will all work. And then you pull the liner down and find out the ribs running right through the middle of all of that stuff. So, no. And the VSWR between the whips and the dual bands is pretty close. Okay. So, I mean, I didn't do any serious study on it, which is interesting. But again, getting back to using stuff on VHF, if you're going to mag mount an antenna on a vehicle, and you've got it at the edge of the vehicle's roof, it's just not going to work well. VHF really wants, you got to have a quarter wave, right? It's going to be 18 or 20 inches around that antenna if it's going to work worth a hoot. And this got back to our vehicle clinic, which I think we're planning on doing again this year, not finding any VHF installs that were good. And, I love running VHF. I think it's a really great solution for a lot of reasons, but man, you've got to be on your game to make it work.
Yeah, so don't have a big glass sunroof in the middle?
Well, so that's the other problem is, try to order a vehicle without a sunroof.
Yeah.
And that's
hard.
it's really hard. You know, everybody wants sunroofs. I'm not a sunroof guy. You know, if I overturn the vehicle, I really want some steel there. And on top of that, if I'm going to mount a bunch of antennas, glass doesn't work too well. So anyway, thank you all for your time today.
Just a reminder that there was a great presentation about that particular vehicle at an RMHAM university about a year ago. That's on the website if you're interested.